Okay, we start the course with a discussion of data modeling. This is simply a more fancy and a technical term for something that I already introduced in the previous video. And so I brought that slide back to initiate our discussion here. So if you remember from that first video, the setting that we were discussing was somebody making an airline reservation sitting in front of their laptop. They have no idea what the structure of the database behind it is and all that, but they're seeing the information in a form that makes business sense to them for the business function that's being executed. Okay? And the discussion that we had was that behind the scenes, the data that is necessary to support this business function is organized in a certain way. So we said that there's customer data, flight data, route data, aircraft data, and so forth. And the important point that we made was that this collection of data or the database must be structured in some way. It must have some structure to it. Okay? And in fact, we defined a database as a structured collection of data. And we had reasons for why we need structure to the database. But a data model is simply a description of the structure of the database. Okay? For instance, in the picture that you see here, the data that's being used to support the application, the booking application, is organized as 4 different pieces. So there's customer data, flight, route, aircraft. But you can easily think of other organizations. For instance, why isn't the aircraft data and the route data just grouped together as one piece? Customer data is another piece, flight data is a third piece. So instead of having 4 pieces, have 3 pieces. So there are pieces, there are components to the data, and of course there's relationships among the different components. That's what makes up a structure. If you think of the structure of a building, every building has doors and windows and things like and floors and so forth. But each component is slightly different from building to building, and the relationships among the components are different as well. So a data model is simply a description of the structure of the database. Okay? Now, data modeling is the process of coming up with that structure based on business characteristics. How does the business function? What are the information processing needs and so forth? So based on those needs, coming up with the structure, the conceptual structure of the database is the process of data modeling. And we won't learn it in 1 week. We'll just start a discussion now. Our journey through data modeling will take at least 3 to 4 weeks now, and then we'll come back to it at the end of the course actually. Okay, so to recap our starting discussion here, a data model is simply a conceptual description of the structure of the database. Okay, and data modeling is the process of coming up with that structure. Now, there are many different ways of describing the conceptual structure of a database. One way is what I'm doing right now, that is verbally and informally describing it to you. So I went through a narrative where I said the database has 4 pieces here. There's customer data, there's flight data, there's route data, aircraft data, and so forth. And I'm giving you a verbal description of it. Obviously, it's informal. Now, this kind of a description may be nice to inform a layman, but you can easily see what the deficiency is. It is absolutely not precise enough, and it can provide absolutely no guidance for implementation. So if you're in the process of implementing a database, this kind of verbal natural language narrative is completely useless as a data model. Okay? So we need to look at something more precise. Okay? And that's what this journey of this week and the next 3 weeks or so will be. It's a process of understanding what constitutes a data model and what is the process of coming up with a data model. So some of the questions that we will answer this week or address this week and the subsequent 3 weeks or so, I already explained to you what is a data model. And of course, we need to have a little discussion of why is a data model important. So being able to describe the conceptual structure of the database allows us to understand whether or not it will do a good job of meeting the business information needs, both in terms of efficiency and effectiveness. Okay, so will I be able to access the data that I need? If you think of the airline example, will the structure allow me to retrieve passenger information that I need to get? Will it allow me to access retrieve data on route information? Can I make changes efficiently to the database? Most importantly, what will be the quality? Will there be integrity of the database? For instance, it would be an absolute disaster if I change my phone number in my profile and it shows up in my profile but not in my booking. Okay, so if I have inconsistencies of that sort in the database because of a poor conceptual structure, that's bad news. Okay, so the structure of the database, in other words, the conceptual structure, the data model, is absolutely important in determining whether it's effective and efficient in meeting the business information processing needs. So obviously that also gives rise to the question, how do we know that a structure is good? So we go through the modeling process, we go through a process and come up with a structure. Then how do we know that it's any good? So that's also a discussion that we are going to have. Again, it's a discussion that will continue for some time. It's not something that will be mastered in 3 or 4 weeks, but it's a discussion that needs to be had. Okay? And then last but not least, this data modeling process, what are the different stages? Of course, it's a systematic process. You can't do it all in one leap. In other words, going from a business description of this is the information that I need, this is the function that I need to support, going from that stage to actually the nitty-gritties of the database. It cannot be done in one fell swoop. There's a discipline to it, and there are different stages of the database modeling and development process. So we'll also have a discussion of that in our journey through data modeling. Okay, so that's sort of the plan of action here, not just for this week, but also for the subsequent 3 weeks or so. So to motivate a discussion on structure, again, we'll come back to the example that we had used the first time around. So the starting point for discussion is, why discuss structure at all? Why not put everything, all the information that I need for the application? Why not put it all into one big list? So think of this as one humongous spreadsheet, okay, just one big list. So for our airline example, why not take, why have 4 pieces of data? Why have separate pieces on customer, flight, routing, aircraft? Take all that information and just put it in one big list. Okay? So from that starting point, once we understand why this one humongous big list may not be desirable, from a structural standpoint, why it might have deficiencies, then we can progress to the next step, meaning how do we come up with a good structure? Obviously, if everything in one big list doesn't work, then it makes sense to look at more involved structure. If a big list would have been fine, then there would be no need to discuss structure. So it is important to understand what are the deficiencies of putting all your data in one simple list, one big list. Okay, so that's where we would start our discussion. Now, since this airline example is much too complex for initiating a conceptual discussion, there's too much information here to handle, we'll start a discussion of this why not one big list discussion with a much more simple example. So in this example database that we have information on students and faculty advisors. So imagine that this database is keeping track of students and their academic faculty advisor. So the kinds of things that we might want to do with a database like this is, we might, for a particular faculty advisor, we might want to know who are all the students that this faculty advisor is advising, or for a student, we might want to know who is the faculty advisor of this particular student. So these are the kinds of questions that you might want to ask of a database like this. In terms of manipulating the database, you might want to add a new student, you might want to add a new faculty advisor. Let's say a student leaves this university, you might want to delete the student from the database. If a new faculty member arises, you might want to add a new faculty member. So think of this database, this one big, putting everything in one big list over here. Also try to think about what are the functions that one might execute on this database. So that's also something to keep at the back of your mind. So what kind of information do we have in this one big list? Obviously, we have the names of the students. You can see it in the first column over here. We have their email addresses, and we also have their majors. And notice one thing, Mia Hernandez, this particular student, is a double major. You can see that their major is MIS as well as finance. So that's a student with a double major, which can happen. And then the faculty advisors, here are the faculty advisors, their names, and the faculty advisors' email, and the accounting, the department of the faculty advisor. Now also notice one thing, the data can speak to you, it can tell you things about the nature of the data in this database. So as you see, Sophia Barnes' names 3 times here, 1, 2 through. So that means this particular advisor is advising 3 students. So one faculty advisor can advise multiple students, which makes sense. That's what typically what happens. Now, similarly, in the case of Mia Hernandez, notice that the MIS advisor is one particular person, the finance advisor is somebody else. Okay, so this particular student, Mia Hernandez, has 2 advisors, not for the same major, but for her different majors as 2 different advisors. So when you just take a look at this one big list, all the data that we need for this application in one big list, you get a sense of what is going on behind the scenes. And as I said a minute ago, try to keep in mind also the kinds of operations and activities that you would do on this very simple database. Okay. So now let's start a discussion of why this one big list approach, putting everything, that is not worrying about structure, putting everything in one big list, why that might have problems. So even for this simple database, let's say what we want to do is add a new student. So here you have this new student, Sun Kim. We know the address, the email address is sunkim@myuniversity.edu. We want to add this new student. And notice that it would be difficult to add this new student until we also know their advisor. So we still not yet don't know their advisor yet, and it would be hard to add this information. In other words, it's difficult to add the new student until we also know their advisor. Okay, this is technically what is called an insert anomaly. The reason that arises from time to time is that you don't have all the information that you need in order to to add that particular record into the database. Okay, so going back to our airline example that we started off with, the more complicated example, the analogous situation in the case of the airline was, let's say an airline introduces a new route. So they introduce a new flight, let's say between Washington, D.C. and Los Angeles. Okay, so that's a new route that they want to fly. So by this, the analogous situation was the airline would not be able to add information about that route into the database until and unless at least one passenger makes a booking on that route. Okay. So that's obviously a weird situation to be in. An airline should be able to add that information into the database, even though there is no customer who has currently made a booking. Okay. So this is an example of an insert anomaly, and this is one of the problems that can arise when all the information that you need for your database is put into one big list. So this is one of the issues with the one big list approach. Okay, let's see some of the other issues that can arise with this one big list approach. Now let's see the second problem called an update anomaly. Again, it's a fancy name for something that can arise fairly frequently. So here's the situation that arose. So the first situation here is Mia Hernandez got married, okay, and her name changed to Mia Johns Hernandez. So, however, since her name appeared in 2 different places in that list, in one record the name appears as Mia Hernandez, the prior marriage name, and in the other record it appears as the updated name, Mia Johns Hernandez. So you have an inconsistency in the data. So the same person, the name should be the same in both places. Okay, so this is a consequence of redundancy, and the redundancy arose simply because you put all the information that you needed for the database in one big list. Because Mia Hernandez is a double major, by putting everything into one big list, you had to list her name twice. And in the process of doing that, you opened yourself up to the possibility that there might be inconsistency in the record. The same thing here with faculty advisor Sophia Barnes. Sophia Barnes' names changed to Sophia Barnes Smith, and in 2 places the name appears as Sophia Barnes Smith. In 1 place it appears as Sophia Barnes. That's not nice. Okay, that's having inconsistent in the database is not nice. Okay, so one of the consequences, a second bad consequence of having everything in one big list is this thing called an update anomaly, and it arises due to redundancy. Okay? So going back to the airline example, what might happen is that if you put all these customer, flight, route, aircraft information in one big list, imagine the situation where the price for a particular flight changes. The prices for flights change all the time. So The analogous situation would be two persons spot the made reservation on the flight. In one case, a certain price appears. For the other passenger, a different price appears. So the revised price didn't get reflected everywhere that the price should show up. Okay. Obviously, that would be a problem from a business standpoint. You would have complaining customer, okay, that your same flight in different prices being charged for the same product, different prices being charged. So a second bad consequences, unfortunate consequence of putting all your data into one big list without designing a particular structure is this thing called an update anomaly, and it arises because of redundancy in the data. And I think you can easily extend this discussion to other applications. I have had situations from a bank where I had a checking account and I had a certificate of deposit. Also, I changed my address. It got changed in the checking account because I interact with it regularly. It didn't get changed in the certificate of deposit. So when the certificate matured, the maturity notice went to my old address, not my current one. So there are business consequences. This is not just a nice technicality. Oh, the names are different in two different places. There can be real, unfortunate, undesirable business consequences of this kind of anomalies in the database. So it's worthwhile to go through an understanding of what makes for a good database structure. Let's see some other. Okay, let's look at yet another problem that can arise if you put everything, all your data into one big list instead of structuring. So what happens when a student, the technical problem is called a delete anomaly. So let's see what that means in this particular example. So Mia Hernandez leaves the university. So if the Mia Hernandez leaves the university, she's a double major. So both these two records are deleted. Okay, so let's see what the collateral effect of that deletion. So Mia leaves, that's fine. So Mia's record is gone from the database. That's well, and there's nothing wrong with that. Now let's look at, as a sort of byproduct, what happened. The faculty advisor name also went because the record was deleted. All right. So Jacob Peterson's name got deleted, as did Chris Tran. Now, what is the difference between these two faculty names being deleted? Jacob Peterson also happens to advise somebody else, that is Ethan Johnson. So the fact that Mia Hernandez left and this particular Jacob Peterson got deleted is not a problem because the database still remembers the fact that Jacob Peterson is a valid advisor. Okay, so that particular deletion had no problem. But this first one, this Mia Hernandez for the MIS, when Chris Tran got deleted as a consequence of Mia Hernandez leaving, Chris Tran's only advisee was Mia Hernandez. Chris was not advising anybody else. So as a result of Mia's record being deleted, the information that Chris is a valid advisor also got deleted in the process. Okay, sort of collateral damage, you might say. All right, that's not desirable. The analogous situation in the case of the airline would be that if the only customer who had made a reservation on a particular flight canceled that reservation, then that flight information would also get deleted. Obviously, that's an absurd thing to do. Okay, so this problem is called a delete anomaly, and that is also not desirable. And the reason it arose is because of putting everything in one list, okay, and not structuring your data appropriately. So I hope you saw that these three problems, insert anomaly, update anomaly, and delete anomaly, are undesirable characteristics that properties that can arise if you put all your data in one big list. So this simple-minded one big list approach usually does not work well, except for the most simplest sort of trivial circumstances. Okay, so let's proceed with this discussion further. Now that we know what problems can arise if you put everything in one big list, that simple-minded approach, now what can you do about addressing those problems? So to elaborate on the discussion, we've already discussed update anomaly, and we said that it is due to redundancy. So Mia Hernandez appearing twice was the cause of the update anomaly. Sophia Barnes' name appearing more than once was also, so the redundancy was the cause behind the update anomaly. So All student information repeats each time because we put everything in one big list over here. If you have double majors or triple major, then their name would appear multiple times, and you have the possibility of an update anomaly. So how can we avoid this? Similarly, in the case of Sophia Barnes, Jacob Peterson, their names and email addresses appear multiple times. Now, how can we avoid this kind of redundancy? How can we go about doing that? These are things that we will be discussing next. In the case of the insert anomaly, where you remember we were trying to add a new student and we were having difficulty doing that because we didn't know the name of the advisor. We didn't have the complete information that we needed in order to add the information. Now, how do we address insert anomaly? Perhaps we could try and find out what are the business rules of the university. For instance, must a student have a major? So when a student enters a university, do they have to declare a major? And must they be assigned a faculty advisor prior to being admitted? Okay, so these are sort of business rules. These are called business rules. Or you must know something about the application, the domain for which you are trying to build the database. So that kind of information can help you in the next stage where we will try to come up with the structure of the database. At this point, the only discussion that we are having is why does the simple-minded approach of putting everything on one list, why doesn't that work, and what are the reasons behind it? Once we have an idea of what are the reasons behind those difficulties, then we can take the next steps to address that, to come up with better structures. Okay. A similar situation arises in the case of the delete anomaly. The delete anomaly and the insert anomaly are sort of flip sides of the same coin. In the case of the insert anomaly, you couldn't add something because you had incomplete information, and in the case of the delete anomaly, by removing something, you have collateral damage and some undesired, some information that ought to remain in the database gets removed as a result of collateral damage. In this case, it was Chris Tran. By Mia Hernandez leaving, the fact that Chris Tran is an advisor, that information also got removed. Okay. So the relationship between the student and advisor, whether they must have an advisor and so forth, those are unclear at the moment. So these are things we need to sort out as we work our way towards a more desirable structure. Okay? So the approach to eliminating redundancies or some of the problems about the update anomaly a couple of minutes back, the general approach to eliminating redundancy is to identify different themes for which the data are stored. In the case of the airline database, you remember, if you had put everything into one humongous list, just one list, if we looked at the list, it would be very obvious just by looking at the content of the list that there are different themes in that one list. You would have a theme associated with customers, you would have a theme associated with routes, you would have a theme associated with flights and so forth. So there's some of those subsets of the data that form their own theme would leap out at you, and the general approach to eliminating redundancy is to try and identify those themes and then create separate tables, separate lists for each of those themes. That's the general approach to structuring your data. So starting from that one big list which is not working well, how do we start partitioning it to get rid of some of these problems, the insert, update, and delete anomalies. So let's see the next steps as to how one would go about identifying the different themes and then create the different lists or tables for them. So here we are again with that one big list, and we are trying to identify themes. Now this is a very simple list, so it may be kind of obvious as to what those themes are, but let me point out something that the data will tell you a lot. So by examining the values in the different columns of that one list, it can tell you a lot about what the different themes might be in that one list. But I should also caution you that simply by looking at the data, you may not be able to identify all the different themes. It is necessary to know something about the domain. Okay? For instance, this faculty advising example that we're looking at, perhaps one particular university has a rule that a student must be assigned an advisor at the time that they're admitted. So a student will always come with a faculty advisor once they're admitted. That's let's say, a policy at the university. But not all universities have that policy. Another university might have the policy, let the student come, I know the information about the student, their name, social security number, address, parents' name, and so on and so forth. And we'll assign an advisor in due course. There's no need to assign an advisor right at the moment that the student is entering. Okay? So it is possible that there is a student who doesn't have an advisor. Similarly, you could have an advisor, a faculty member who's qualified to be an advisor who hasn't had any student advisee assigned to them as yet. Okay, so you need to know something about the domain, the particular situation for which the database is being constructed, in addition to having access to the information that's there in the list in order to identify the themes. Now, by looking at when I look at this simple example, I see some sort of groups of themes. Just they sort of leap out at me. For instance, when I think about a student, I can see that student name, student's email, and their major kind of go together. Those three things are associated with a student. Okay? So name of a student, email of a student, and major of a student. Okay, and there are these other things, these other columns that we have don't seem to be characteristics of students. So in my mind, my first cut at identifying one theme that would be there in the list is a theme called student, and the elements, the properties, the columns that make up that theme would be student name, student email, and major, and I would give that theme a name. In this case, given the name student. Okay. Similarly, I see another theme over here, which is faculty. These are the advisors who are advising the students. And for the advisors, I see things like the name of the advisor, I see the email address of the advisor, and I see the department that the faculty member advisor belongs to. Okay, so that to me is a theme. So, for instance, I wouldn't mistake the faculty email as belonging to the theme for student. Okay, similarly, the student's email I would not mistake it to belong to the theme called faculty. Okay? So to me, there is a second theme in this big list, which is the theme that consists of faculty advisor, the name of faculty advisor, the email address, and the department. And these three properties together, or columns together, constitute a theme that I call faculty. Those are the two themes that I see in this particular, but one big list. Now, if you are visualizing one big list that corresponds to the airline example that we discussed, then you could have many more columns, of course, and once you go through those columns, you would probably identify many more themes than just two that we saw over here. Okay, so some themes, when you look at real life lists, some of the themes will be pretty obvious. Some will be not so obvious, meaning that you need to know something about the underlying business application, underlying business rule to extract themes from it. So it's partly art, partly science. So we're seeing some guidelines as to come up with themes, but also remember it is necessary to know something about the underlying business rules and the business application for which the database is being designed. So now let's look at what happens if we apply our guideline, that is, take that one big list, try to identify themes, and create separate lists for each theme. So here we have identified two themes in our discussion that we just had. So those two themes were student and faculty. And here we have the two lists. We have the two lists that correspond to the faculty and the student respectively. Okay. Clearly, you can see that some amount of redundancy has been eliminated. For instance, the faculty advisor's name appears only once. Okay. So Sophia Barnes, Charlotte Hughes, Krista, even though one advisor might be advising multiple students, by dividing off, by creating these two themes which constitute the one big list, at least some of the redundancy that is gone. So, for instance, if one of the faculty members gets married or for some reason, their name changes, Sophia Barnes' name changes, there is no likelihood of inconsistency because the name only appears in one place, the change will be made in one place, and it will be good. You wouldn't have to worry, that name might be appearing somewhere else, and I might have fouled up and not changed the name in all the places. So the update anomaly at least partially goes away. It's not completely gone, because if you look at the list for students, you can see that Mia Hernandez, because she's a double major MIS in finance, her name appears twice. Okay, so there is still, even though we created two themes, there is still the possibility that if Mia Hernandez's name changes as it did after being married, you could get inconsistency between two places where the names appear. But clearly, I hope you would agree that taking this one big list and breaking it up into two lists based on the themes that are there in that one big list at least has reduced the inconsistency, the anomalies to a good extent. Again, here another thing that you can see: if a student enters the university and they don't have an advisor, you would be able to put that student in this particular list, the student list, and you wouldn't need to also know the faculty advisor name if you don't know that. Similarly, if you have a faculty member who's qualified to be an advisor but doesn't have an advisee at the moment, you would just add the advisor here on that list without having to worry about, is there a student that goes with this particular faculty. So I hope you're beginning to see some of the benefits that are arising as a result of this structuring of the data. We started with one big list that was not working well, and we, based on the themes present in that list, we broke it up into two lists, and we are gradually improving and addressing the issues that were there with that one big. Now, we have addressed some issues by creating the two lists based on the two themes, but we have also created a problem in the process. That is, yes, we have two lists now, so how do we put Humpty Dumpty back together again? So how do I create that one big list after having split it up into two? It's not enough to split the one big list into two smaller lists to get rid of the update anomaly and insert anomaly and so forth. I must be able to recreate that big list, because the one big list is what told me who advises who. If I look at these two lists in isolation, there is no way for me to tell at the moment, based on how it looks right now, there is no way for me to tell who Mia Hernandez's MIS advisor is. There is no way for me to tell who Noah Turner's MIS advisor is. There is no way for me to tell who Olivia Rogers' accounting advisor is. So the connection. So these two lists are related. Okay. So it's a structured collection of data. Remember the example that we said, by structure we mean what are the different pieces and what are the relationships among the pieces. So anytime you hear the word database structure, I think it's a good analogy to think about buildings and the architecture of buildings. Any building has a structure. We say buildings have structure. What do we really mean? We mean what are the different pieces. So there are windows, there are doors, there are balconies, etc., and how are those pieces related to one another. Some buildings have balconies at the back, some have balconies in the front, some have balconies at different levels. So I hope you get the picture in terms of what we mean by structured pieces and relationship among the different pieces. So what is missing from this picture is what is the relationship between these two pieces that we have created. By creating these two pieces, we have addressed some problems, namely the insert, update, and delete anomalies, but we have created a problem in the process. That is, we need to put Humpty Dumpty back together again. So we need to be able to connect the related data between the tables, and the relations between the themes in that process need to be identified. That's what we're going to do. Okay, so in terms of identifying the relationship, in this example, we have only two themes. So obviously, we look for relationships between just those two themes. But in a practical situation, let's say by looking at the one big list, you identify 5 or 6 themes. Then the first thing you would need to identify is which pairs of themes are related with one another. Not everything will be related with everything else. So if you have multiple themes, let's say 6, 7, 8, 9, 10 themes, you need to identify which themes are identified with one another. Okay. So here, and the way you do that is by looking at the content of the data. So here we can see, let's see here, Olivia Rogers has Sophia Barnes as their advisor. We knew that from the one big table. Okay? So these arrows that you're seeing connect students with their respective advisors. And how did I get these connections? It's from that one big list. So when you look at the one big list, it would show you which faculty member is the advisor for a particular student. That's where these links come from, and I would be able to say which students are associated with which advisors. Okay, and in the process, once we have established that there is a relationship between these two particular themes, we identify a parent and a child for each relationship. Okay? What does that mean? Parent data can exist without related data in the other. Child cannot exist without the related data. So what does that mean? It means that you could have, in this particular situation, knowing what I know about how universities work. So here again, a little bit of domain knowledge is important. So I can see that one faculty member can advise multiple students, and there could be a faculty member who does not have an advisee yet. Okay, so that tells me that the theme called faculty is a parent. Okay, so a parent can exist without related data, meaning you could have a faculty member who is potentially an advisor, but at the moment doesn't have any advisors. Okay? Now, a child cannot exist without related data. So here we have a student cannot exist without a particular without an advisor. Okay? So if there's a student, they must have an advisor. And this again, this is not a universal truth. This is something that we see from the data, and perhaps it's the policy of this particular school or university that every student must have an advisor for that particular major. Okay? So this parent-child relationship between themes is something that needs to be identified to be able to put Humpty Dumpty back together again. Now, once you have identified the relationship, how do you implement it in the database itself? That's what we will see shortly. So, as I just said a moment ago, these two themes are related. So, in this slide, we're just recording the relationship that we discussed a couple of minutes back. Namely, these two themes, students and faculty, they have a parent-child relationship between them, and we figured that out based on looking at the data and also our knowledge of how the faculty and student advising relationship works. So, data for student cannot exist without related advisor information. So that makes student that theme called the student makes that the child. And data for faculty can exist without related student information. Meaning you could have a faculty member who does not have an advisee yet. Okay, that makes this theme called the faculty the parent. So I hope you're seeing this process of gradually decomposing and coming up with the structure of the database. We started off with everything in one big list, and then we said, oh, it has issues. There's insert, update, and delete anomaly, and the approach to addressing those anomalies is to find themes and disaggregate this one big list into different themes. That took care of the anomalies, but it gave rise to another issue, that is how do you put things back together again with losing the relationship. So finding the relationships among the different themes is sort of the next piece of the puzzle in coming up with the structure of the database. And this parent-child relationship is one piece in terms of identifying the relationships among the different themes that might exist. So this simple example has only two themes, so the relationship is fairly obvious. If a relationship exists, it has to be between the two themes. And the other thing to remember is that if there was no relationship between these two themes, then of course they wouldn't be part of the same database. A database is a collection of related objects, related themes. If there's no relationship among any of the themes, then it doesn't make sense for them to be part of the same database. So now that we have identified the fact that there's a parent-child relationship between the faculty and the student in this example, how do we actually implement the relationship? So here in this slide, we have shown the relationships by these straight lines. Okay? Obviously, to implement it in the database, we can't draw lines in a relational database. But how do we implement it? We implement the relationship by taking some attribute from the parent theme and adding that to the child theme. Okay? So the choice for a reference column should be something that helps uniquely identify the record in the parent. So what we would need to do in this example is take some column from the faculty theme and add it to the student theme. And the one we would pick should be something that easily identifies the advisor. So as soon as I pick a student, that I identify a student, I say, who's the student's advisor? That reference column that I will add a column here to this table, should be something from the parent that easily identifies the parent. Okay. Now, if I look at this particular theme called faculty, the faculty advisor name would not be a good reference column, because you could have two advisors with the same name, same first name, same last name. Okay, so picking the faculty advisor name as a reference column would probably not be a good idea. However, we do know that each faculty member has a unique email ID, so it would probably be better to use the faculty member's email ID as the reference column. Okay. So this is how the reference column would look. We would take the faculty member's email ID and add it as extra column to the student theme. Okay. So let's say I want to know who is the advisor for Noah Turner. I would look at Noah Turner's record, and I would see this email address over here, and I know that's my link to the parent, and I follow that to the parent, and I say, who is this particular advisor? So I look at C. Hughes. Where is C. Hughes? Here is C. Hughes. And that's how I know that Charlotte Hughes is the advisor for Noah Turner. So this is the technical implementation of this arrow that you see. Okay. So this reference column that you see is the way of connecting. This is what we put Humpty Dumpty back together again. So even though I broke up that one big list into smaller lists to take care of anomaly, I need to be able to put the relationship back. I can't lose the relationship between advisor and student in the process of breaking up those two themes. Okay, so I hope you get the idea of what a reference column is and how that is used to capture the relationship between parent and child themes. So pictorially, the themes that we have identified and the parent-child relationship that we have identified, how do we show it pictorially? Now, so you show the two themes with the names on them, the columns that make up that particular theme. So in this case, student has 3 columns: student name, student email, major and advisor email. Notice that the reference column is also included in the theme. Okay, it's the reference column that allows me to link the child back to the parent. So faculty is the parent, and the columns that make up the faculty theme are faculty advisor, faculty email, and faculty department. Okay, and pictorially we can show a line connecting the parent and the child, and we write down which one is the parent and which one is the child theme. However, in terms of implementing it, if you have to implement it in the database, what would tell me which advisor is which, linked to which student, is this reference column over here. So notice that this reference column is an integral part of this structuring process. So I decomposed that one big list, into smaller lists to take care of anomaly. But in the process, I was losing information about relationships, and to get that back, I identified parent-child relationships among the different themes and implemented that relationship through the use of reference columns. So in terms of summary, what have we learned? We learned of the concept of a data model. It's simply a conceptual way of describing the structure of the database, and we said that just describing the structure of the database informally through English narrative is imprecise, cannot be used for implementation. So we need to come up with some other ways of coming up with the structure of the database. And remember, the word structure simply means what are the components of the whole, and what are the relationships among the different components. So, and that same logic applies to structure of cars, structure of houses, structure of databases. What are the components? How are the components related to one another? Okay, so we saw what problems can arise as a result of not structuring your database, putting everything in one big list. So you had the insert, update, and delete anomalies. So it's important to understand what those anomalies are and why they arise. And the fix for that is to decompose the one big list by identifying themes. And we said that how do we go about identifying themes? Part of it is by looking at the data itself. The data will tell you where the themes are and what those relationships might be among the different themes. But it's equally important to remember that you also need to have a knowledge about how the underlying business works. Okay? For instance, it may not be always possible when looking at the data to say with absolute certainty that every student must have an advisor. Okay, something that we did in this particular example. That's something that we know from the domain, but we also saw in the example that every student had an advisor, so it would be reasonable to conclude that a student would need an advisor. Okay, and in the process of taking care of these the problems with putting everything in one big list, we saw how we decompose them into themes, and we also saw how to implement the parent-child relationships among the different themes using reference columns. Okay, so these are the basic concepts associated with our, at least the initial concept associated with our journey through data models, and we will continue this journey in subsequent weeks. Look at other ways of creating or generating the structure of a database. Not all of them involve starting with lists and decomposing them. So we will see what they are, but this discussion should help us get started. At least it should convince you that the simple idea of putting everything in one list, thereby not having any kind of structure, doesn't work very well.